Welcome back to G Fun Facts Online. Today we are stripping away the introductions and diving straight into one of the most mind-bending headlines to come out of the physics world in recent years. We are talking about time. Specifically, we are talking about negative time. You have probably heard the old adage that time waits for no one. It is a one-way street. Cause comes before effect. You enter a room, and then you leave it. You cannot leave the room before you enter it. That is just how reality works. Or at least, that is how classical reality works. But in a basement laboratory at the University of Toronto, a team of quantum physicists, led by Professor Ephraim Steinberg and doctoral student Daniela Angulo, has just demonstrated that in the quantum realm, these rules do not apply. They have provided the first experimental evidence that photons, particles of light, can spend a negative amount of time interacting with a cloud of atoms. This is not a simulation. This is not a mathematical trick. This is a physical observation, where a particle effectively finishes a task before it has even started. Today, we are going to break down exactly how they did this, why it does not actually break the laws of physics or violate Einstein's theory of relativity, and what this means for the future of our technology. To understand why this experiment is so groundbreaking, we first need to establish a baseline for how light usually travels. Imagine you are driving a car into a tunnel. If that tunnel is 60 miles long and you are driving at 60 miles per hour, physics dictates that you will emerge from the other side exactly 1 hour later. If there is traffic inside the tunnel, let's call that resistance, you will emerge later than that. In the world of optics, when a photon travels through a material like glass or water, it interacts with the atoms inside that material. The photon might get absorbed, it might excite an electron to a higher energy state, and then be re-emitted. This bouncing around takes time. Physicists call this duration group delay. Because of this atomic traffic, light usually travels slower through materials than it does through a vacuum. The group delay is positive. You go in, you spend time interacting, you come out later. That is the classical expectation. But the team at the University of Toronto wanted to test a theoretical prediction that under very specific, extreme conditions, this group delay could become negative. To do this, they couldn't just use a piece of glass. They needed something much more controllable. They built an experiment using ultra-cold rubidium-85 atoms. When we say ultra-cold, we mean they cool the cloud of these atoms to within a hair's breadth of absolute zero. At these temperatures, the atoms are nearly motionless. This creates a state of matter where quantum effects become macroscopic and measurable. This cloud of rubidium atoms served as the tunnel. Here is how the setup worked. They fired what they called signal photons at this cloud. These photons were tuned to a frequency very close to the resonance of the rubidium atoms. This is the car entering the tunnel. But here is the problem. How do you measure how much time a photon spends inside an atom? You cannot simply click a stopwatch when it enters and clicks it again when it leaves, because in quantum mechanics, the act of measuring usually destroys or alters the state of the particle. If you measure it too harshly, the wave function collapses and the experiment is ruined. So the researchers used a technique called weak measurement. This is a concept pioneered by physicist Yakir Aharonov, and it is a specialty of Professor Steinberg. Instead of a hard measurement, they used a second laser beam, called the probe. This is the stroke of genius in this experiment. Through a quantum phenomenon known as the cross-Kerr nonlinearity, the probe beam would experience a tiny, almost imperceptible phase shift, a change in its wave pattern, whenever the signal photon was inside the atoms. Think of the probe beam like a security camera monitoring the tunnel. It records a tiny blip on the tape every time the car is inside. By analyzing the phase shift of this probe beam, they could reconstruct exactly how much time the photons spent interacting with the atoms. And when they ran the numbers, the result was undeniable. The probe beam measured a phase shift that corresponded to a negative interaction time. The data showed that the atoms spent a negative amount of time in the excited state. In plain English, the photons were traversing the atomic cloud and exiting it faster than if the atoms hadn't been there at all. It was as if the photons had exited the medium before the atomic excitation process had even finished. Now I know what you are thinking. This sounds like time travel. It sounds like the photon arrived at the exit before it entered the entrance. And whenever we hear about things moving faster than light, or happening in negative time, the ghost of Albert Einstein appears to wag a finger at us. Special relativity strictly forbids information from traveling faster than the speed of light, which we denote as circa. If you could send a signal faster than light, you could theoretically send a message to the past, which would violate causality. So did the Toronto team break the universe? No. And the reason why is one of the most subtle and misunderstood concepts in physics: the difference between group velocity and information velocity. To understand this, we have to stop thinking of a photon as a single hard bullet. A pulse of light is actually a wave packet. It is a collection of many different frequencies bunched together, shaped like a bell curve. This bell curve has a front, the very leading edge, and a peak, the highest point of the curve. Special relativity says that the front of the pulse, the very first precursor of the signal, cannot travel faster than light. That front contains the actual new information. However, the peak of the pulse, the part we usually measure to determine when a signal arrives, is malleable. In what physicists call anomalous dispersion media, like this ultra-cold rubidium cloud, the different frequencies that make up the pulse interfere with each other in a strange way. The back of the pulse might get absorbed more than the front, or the phases might shift in such a way that the peak of the wave packet gets reconstructed forward. The result is that the peak of the pulse exits the material before the peak of the pulse enters it. The front of the pulse, however, still obeys the speed limit. For decades, physicists argued about this. They said, sure, the peak moves forward, but does that represent physical reality? They argued that this negative group delay was just a mathematical trick, a reshaping of the pulse, and that the photon didn't actually spend negative time in the atoms. This is where the Toronto experiment changes the game. By using that probe beam to measure the atomic excitation directly, they essentially asked the atoms, how long did you feel the photon? And the atoms replied, negative milliseconds. This confirmed a theoretical prediction made by quantum physicist Howard Wiseman. The experiment proved that the dwell time, the time the particle actually spends interacting with the barrier, is physically equal to the group delay, even when that delay is negative. It is not just a reshaping of the pulse, the physical interaction itself carries this negative value. The history of the particle involves a negative duration. This leads us to the concept of the quantum clock. To understand how a clock can run backward, we have to abandon the idea of time as a rigid, linear ruler. In this experiment, time is a quantum observable. Imagine a stopwatch that runs only when a photon is inside an atom. In a classical world, the hand moves clockwise, 1 millisecond, 2 milliseconds, 3 milliseconds. But in the quantum world, the photon is in a superposition. It is simultaneously transmitted, reflected, and absorbed. When these different probabilities interfere, the average position of the clock hand can end up behind where it started. Professor Steinberg uses a great analogy to explain this. Imagine you are watching people enter a store. Most people spend 10 minutes shopping. Some people get confused, spend 1 minute and leave. But in the quantum store, you can have a situation where the people who leave are the ones who, on average, unshopped. It implies that the photons that made it through the cloud were the ones that arrived at the exit too early, effectively borrowing energy and time from the vacuum in a way that the mathematical average of their interaction became negative. This experiment is not just an isolated curiosity. It is actually the climax of a scientific controversy that has been raging since the 1930s, known as the tunneling time problem. In 1962, a physicist named Thomas Hartmann calculated how long it takes for a particle to tunnel through a barrier it should NT be able to cross, a quantum wall. He found something shocking. As the wall gets thicker, the time it takes to tunnel doesn't increase, it saturates. This became known as the Hartmann effect. It implied that for a thick enough wall, the particle would cross instantaneously. For 60 years, we have debated how to define time in this context. Is it phase time? Is it dwell time? Is it Larmor time? The Toronto experiment has effectively connected these dots. By showing that the atomic excitation time is equal to the group delay, even when negative, they have solidified the link between the pulse's arrival and the particle's interaction. They have proven that these impossible negative numbers are not errors. They are the correct physical description of the event. So, why does this matter? Beyond the philosophical thrill of realized negative time, this discovery has tangible implications for the future of technology, specifically regarding the quantum internet. We are currently trying to build networks that can send information via photons through optical fibers and store them in quantum memories, without destroying their delicate quantum states. Understanding that interaction times can be negative allows engineers to better model the noise and loss in these systems. If we do not account for these negative delays, our error correction algorithms for quantum computers might fail. Furthermore, the technique used weak value amplification is incredibly sensitive. The fact that the researchers could measure such a minute phase shift resulting from a single photon's interaction paves the way for sensors that can detect the presence of single atoms or faint chemical signatures with unprecedented accuracy. There is also the potential for all-optical switching. If we can manipulate light to traverse a medium with negative delay, we can theoretically create optical switches that operate faster than the transit time of the material itself. While we cannot send information back in time, we can minimize the lag in optical circuits to zero, or seemingly less than zero, pushing the speed of optical computing closer to its fundamental limits. The observation of negative time serves as a stark reminder that the universe does not run on human common sense. It runs on quantum mechanics. In our macroscopic world, cause always precedes effect. But when you zoom in to the level of a single photon, those rigid rules soften into a haze of probabilities. A photon can be in two places at once. It can traverse two paths simultaneously, and now, thanks to the work of Steinberg, Angulo, and their team, we know it can finish an interaction before it starts. This experiment transforms a mathematical quirk into a measurable, physical reality. It tells us that negative time is not just a sci-fi trope or a calculator error. It is a legitimate coordinate on the map of the quantum world. As we peer deeper into these anomalies, we aren't just learning about light and atoms, we are learning about the fundamental texture of reality itself. And sometimes, to move forward in our understanding, we apparently have to move backward in time. That is all for today's deep dive on G Fun Facts Online. Thanks for listening.